Okay, hopefully everyone can see. I see that it's probably about half the people here are from my group, so probably a lot of this is going to be quite familiar. So yeah, thank you for giving me the opportunity to talk today. So I'm going to talk about the simulations I've been working on of accreting neutron stars and how they relate to pulsating ULXs. So this is a mix of projects I've been working on for the past several years. With me and my supervisor, Wojtek Kluźniak, and also collaborating with Kyle Parfrey from Dublin. Okay, so let's get into it. Okay, so pulsating ultraluminous X-ray sources. So to talk about these, first we have to talk about accretion disks. And so for anyone who does not know, accretion disk is when you have a compact object which is absorbing matter. Maybe it's in a binary system and mass is flowing near the star, and it forms a disk and eventually falls onto the central object. Now, accretion disks can be very bright, and the rate at which they convert the inflow of matter to energy is known as the efficiency rate. And accretion disks can have incredibly high efficiencies, around 1/10. So they're basically the most efficient energy extraction process we have in the universe, besides matter and antimatter annihilations. Okay, a good measure of this luminosity, and just sort of a very useful unit, is the Eddington luminosity. So the Eddington luminosity is basically proportional to the mass of the accreting object. And what it corresponds to is the maximum luminosity that a spherical source can have due to the balance between gravity and radiation pressure, because the radiation will move out and gravity pulls things in. And if something is too bright, then it ends up blowing itself apart. Now, the Eddington luminosity doesn't necessarily apply to accretion disks because they're not spherically symmetric. However, it is useful to get an idea about what regime we are. And in order to do that, we introduce something called the Eddington accretion rate. So the Eddington accretion rate is basically, if you take the luminosity, the Eddington luminosity, and you figure out, how much matter, what's the rate of mass accretion that we need to produce one Eddington luminosity, that's the Eddington accretion rate. And this efficiency, people actually use different numbers for this. There's a difference between, the true efficiency, how much luminosity is actually produced, and just this, this efficiency that I throw in there sort of as a yardstick, as a unit of measure. So normally I'm using like 1/10 or 1/16 or something. And it's important because we can divide accretion disks into different regimes, scaled by this Eddington accretion rate. Okay, so in the sort of middle of the range of accretion rates, and this is anywhere between, and this is really rough, between 10 to the -4 of these Eddington to about less than 1 Eddington. This is where we usually think of the standard Shakur-Senyaev thin disk solutions, or Novikov-Thorne if you're working in relativity. So the idea here is that the disk is optically thick, so it can cool very efficiently, and radiation is released as soon as it's generated. Okay, so this allows it to cool and become very thin. At the lower end of the accretion rates, what happens is the disk becomes optically thin, so it cannot cool efficiently. So it becomes very hot and starts to puff up, not to be confused with a puffy disk, but it starts to get thick and has very, very low, actual efficiency, something like 1/100, something like this. So they're very dim and thick, and this is something that we might imagine is around Sagittarius A star, for example. At the high end, and this is what we're going to talk about today, is when you get more than this Eddington accretion rate. And this is called a super Eddington or supercritical disk, depending on who you're talking to. So what happens here is that the disk is so optically thick that the photons, which are generated, cannot escape the accretion disk. They just undergo too many scattering processes before they're absorbed onto the central object. So this causes them to also heat up, and then they expand, due to radiation pressure. And so you have basically, thick disks on either side of this spectrum. Okay, so ultraluminous X-ray sources. So these are the specific accreting object that I'm going to be talking about today. So what these are there's basically, we have an observationally defined definition of what they are. They're just basically bright X-ray objects observed in distant galaxies, but they do not correspond to any AGN, central galactic activity. So these are in the outer parts of galaxies with bright X-ray luminosities that are anywhere between 10 to the 39 and 10 to the 41 ergs per second. So if you think about the definition of the Eddington luminosity, and you take a 10 to the 40 erg per second source, you might say that you have a 100 solar mass black hole accreting at 1 Eddington luminosity. And that was an early idea for what these objects were. And a competing idea was that we actually, instead of just having sub or 1 Eddington accretion, we have super Eddington accretion onto a stellar mass compact object. So this was suggested by King, I think. So in order to, so one observation, which really, gave us a concrete answer to what these were the observations of pulsations, coherent pulsations of about 1 second in period, observed in the ultraluminous X-ray source M82X2. So what this showed us is that since the source is pulsating, it must have a neutron star at the center. And neutron stars, we have a good idea about what their masses are, something between 1 and 2 solar masses. So if it's producing 10 to the 40 ergs per second, but it only weighs 1 solar mass, we have to be emitting something like 100 times the Eddington luminosity. And there's some additional population synthesis, et cetera, which suggests that probably a lot of neutrons, a lot of ULXs are powered by neutron stars. So the idea is we want to understand this process through simulations. Okay. And just a couple more words about super Eddington accretion. One of the first models of super Eddington accretion actually was in this Shakur Sinayev 1973 paper, but I think most people missed it because it's at the end. And basically what they say is that the extra radiation pressure should drive an outflow such that by the time the gas gets to the black hole, it's only accreting at 1 Eddington. And we see similar results in simulations of super Eddington accretion onto black holes. Very strong outflows are observed. And what is thought to happen is that these outflows, as they're flowing out, are able to collimate any of the emission, released towards the center, so that they look very bright when they're viewed along the poles. Okay, there's some debate out there about the magnetic field strength of pulsating ULXs. Neutron stars have very strong magnetic fields and a very large range of observed magnetic fields. I think we've seen neutron stars with magnetic fields anywhere from 10 to the 8 to 10 to the 15 Gauss at the surface. So some people thought we have, these pulsating ULXs are high magnetic fields. And what happens is that the electron scattering cross-section gets lowered in strong magnetic fields in directions orthogonal to the field, so that you would have sort of a nearly isotropic radiation going on here. So you would have to extract a lot of energy from the gas, because all of a sudden the gas falls into the magnetic field and it becomes optically thin. Also, there was some cyclotron lines observed. And if you say they're due to protons, then that would give you a 10 to the 15 Gauss magnetic field. this same line, if you say it's caused by electrons, would give you a lower magnetic field, 10 to the 11 Gauss. And there's some additional evidence of lower magnetic fields. So what we're going to do is see if we can produce a ULX using a low magnetic field. Okay, now a couple words about beaming. These pulsating ULXs were observed with rather large spin-up rates, and one way you can do that is you have the magnetic field, and then the accretion disk around the magnetic field, and the accretion disk exerts a torque on the magnetic field and spins up the star. But to do this, you have to have a very fine balance between what's called the spherization radius, which is the radius where basically these outflows start to be launched, and the magnetospheric radius, which is the radius where the magnetic field cuts off the accretion flow and forces the gas to flow into columns. So you can from this very specific relationship, you can derive a model, and then you can derive the expected beaming factors from these models. Where a beaming factor, what I mean by that is the observed luminosity of the source is not the true luminosity of the source if you are emitting non-isotropically. So the model basically says that all of the radiation gets concentrated in these cones along the poles. And so we overestimate the luminosity, because when we measure the flux, we then multiply by 4 pi r squared instead of the proper fraction of solid angle, which is from the emitting source. Okay, so the physics involved in super Eddington accretion requires general relativity, it requires radiation, and magnetohydrodynamics. Probably it requires more, but we don't have those in our code. So the equations that we solve, these are just the relativistic forms of conservation of mass, conservation of energy momentum, conservation of radiation, energy momentum, Maxwell's equations. And if you expand these covariant derivatives, you'll see that they all look like conservation laws, okay? And to do this numerically, when you have a conservation law, which is just the time derivative of some quantity is equal to minus the divergence of the flux of this quantity, to do this numerically, you divide space into a grid. And you have some quantity here, Qi, which is your conserved quantity. And then you look at neighboring cells and you decide what's the flux of that quantity in all the cells. And then you just have to, add and subtract all of the flux moving out, all the flux moving in. And then additionally, you could, take into account the source of conserved quantities. So this could be like, in our code, it's the interaction between gas and radiation. Okay, so the interaction between gas and radiation becomes the source, and then you use neighboring quantities, compute the fluxes of the conserved quantities, and you can evolve the thing forward in time. Some specifics of this code. So the code I use is called Coral. It was written by Alexander Sandowski from TOMC. But I think most of it was written when he was at CFA. So it evolves radiation using the M1 closure scheme. So what this means is that we assume radiation acts like a fluid, okay? We take moments of the intensity so that we get fluid-like equations. And this gives us a rank 2 tensor, which is conserved, but we need extra information to compute this whole tensor. And so in order to do that, we say there exists some frame where the radiation looks isotropic. So the pressure part of the radiation tensor, the IJ components of this R mu nu would look like the Eddington tensor, just completely isotropic. But that's in some frame defined by U R mu. So then you can do a Lorentz boost to boost the physics back into the lab frame, and then all of a sudden you have radiation can stream along geodesics, and it works in the optically thin and optically thick environments. The simulations I'm going to run are running 2D axisymmetry. And we use the ideal MHD approximation. So we say in the fluid frame, in the flame of the fluid, sorry, electric fields can be ignored. Okay, and before we get on to magnetized simulations, I did say that we would consider low magnetized neutron stars, but you might ask yourself, what happens if you consider non-magnetized neutron stars? So this is a project I did a long time ago, maybe not long time ago, 3-4 years ago, where we did, similar simulation of accretion onto a black hole and onto a non-magnetized neutron star, which is just modeled by a simple reflecting surface, okay? In the black hole, you can see the outflows being launched, and that creates this funnel is completely empty of gas, and the radiation released in the accretion disk is able to leave the accretion disk along these empty parts. And so the simulation looks very bright when viewed here. By the way, sorry, I didn't mention I'm plotting energy density on the left-hand side, gas density on the right-hand side. If you put a reflective boundary, all of a sudden gas starts accumulating at the inner edge. And this gas traps radiation. That's why we have this big, thick sphere of radiation. And the radiation may look like there's a lot of it, okay, but that's because it's all trapped behind this outflow. And we can actually measure the luminosity as a function of radius by, which I'll explain in more detail how it works later. And we find that the actual luminosity which reaches the observer is, for these neutron stars, is barely half an Eddington. For the black hole, it was about 1.5 Eddingtons. So this is the amount that actually escaped. But what we're interested in is, how bright do the sources actually appear? Okay, so as I mentioned earlier, you usually assume the isotropic luminosity by taking your flux and measuring by 4πr squared, where r is the distance between you and the object you're observing. But the true luminosity, you have to put a factor out in front to represent the actual fraction of solid angle, okay, that you're working on. But if you don't, if you just assume that the luminosity is given by this expression 4πr squared, this is what you would measure. The black hole, most important is the red line. This is basically, if you back up like farther away from the simulation, about 4,000 gravitational radii, then if you're looking along the poles, that's what this number means, is the viewing angle, essentially. You'll see something like 10 Eddington. And then if you look along the plane, in the equatorial plane, you won't see anything. It's basically no radiation. And this neutron star case I mentioned basically appears to be like 1 Eddington everywhere. So this is nothing like an ultraluminous X-ray source. So the black holes can collimate the radiation, but what about neutron stars? It turns out that we can't get there with non-magnetized neutron stars. We need to introduce magnetic fields. So that's what we're going to do. This is somewhat challenging, as I mentioned in the abstract. And one of the reasons why is just the way that the code works. Okay, so this conserved quantities that I mentioned earlier, these are these components of the gas stress energy tensor, and they can be written down in terms of primitive variables, things like the gas density, gas internal energy, pressure, stuff like this, okay? So when you're computing these conserved quantities, you just have to plug in values to this equation here. The problem is you also, during the simulation, have to do the opposite calculation, where you know what T mu nu are, but you want to find things like density internal energy, okay? So if you have in the equation things which are generally very small, like the pressure and internal energy, and things which are very large, like the magnetic field energy density, especially around a neutron star, you get a bunch of numerical errors and it becomes very difficult to do properly. So I collaborated with Kyle Parfrey and introduced his method, which uses elements from force-free electrodynamics to tame the simulation and make it so that we can actually do this simulation. And just to give you an idea about what kind of magnetic fields we're looking at, we have this quantity called the magnetization. Magnetization is basically the ratio of magnetic to rest, at least this definition. There's a couple different definitions. This definition is the ratio between magnetic energy density and gas energy density. So from one of my simulations, I'm plotting here I see I lost the color bar, which is a shame. Dark blue is magnetization of 10 to the minus 4. Dark red is magnetization of 10 to the 4. So we have magnetizations that can reach up to 10,000, and GRMHD codes or GRRMHD codes, this generalistic magnetohydrodynamics codes, start to break down when this simulation is larger than 1. So we really need to use these methods in order to get these regions not to explode, basically. Okay. I can say a little bit how the method works. The basic idea is that we, split the evolution into like this extremely magnetized part, which we treat slightly differently, and this less magnetized part. And in this extremely magnetized part, we basically only allow the magnetic field and the velocity perpendicular to the magnetic field to be evolved. And then the other quantities like the gas energy and gas density and gas energy and the velocity parallel to the magnetic field, those are overwritten in a way consistent with force-free electrodynamics. Okay, so I'm just moving a little bit fast because last time I gave a similar talk, I spent too much time at the beginning. Okay. So how do we set up our simulations? Very typical of accretion disks is to start with a torus in hydrostatic equilibrium and add a magnetic field to it. We also have to add our neutron star magnetic field. In this case, I'm showing you a dipolar field of 2 times 10 to the 10 Gauss. And like I said, I'm doing these in axisymmetry, 500 by 500 cells, and I ran them for about 4,000 G over C cubed. One thing to consider also is the boundary condition. Earlier, I was showing you the reflective boundary condition, and the reflective, like a fully reflective boundary condition is kind of like saying, let's put the boundary condition here. We know that once the gas gets here, it just slams into a hard surface so that we reflect velocities, so that velocity has to go to 0 at the surface. That's one way to do it, but there's very possible that there are radiative processes that happen from when the gas interacts with the the crystal lattice at the surface of the neutron star, that we're not capturing everything, that maybe a reflective boundary isn't appropriate. So you can also do you could say that you have a fully absorbing boundary, and this would be like putting your inner boundary here, letting all the gas fall through and just ignoring all of the radiation that might be released at the surface. But what I decided to do is to introduce an intermediate boundary condition, something that I call energy reflective, where basically the idea is, imagine we put the boundary here, basically, and I measure the flux of inflowing energy, kinetic energy, inflowing radiation energy, and then I return that as an outflowing radiation flux. And then what happens is the outflowing radiation flux slows down the gas, it creates this shock, and then radiation leaves the column perpendicularly. And I also said, well, what happens if some of the gas escapes under the surface of the star and isn't radiated away? Well, we can study this for different albedos or reflectivities of radiation. So we tried everything from 0, which would be the same as the accreting boundary condition, to 1, which would be the same as the reflective boundary conditions. And then a couple values in between. And I just chose the values about where the simulation actually starts to change a little bit. And then we took this 75%, 0.75 albedo simulation, kind of as our canonical simulation, and we ran it much longer and studied it in more detail. Okay, so I will show some movies now. I probably won't show all of them for time, but at first I want to show, hold on. Okay, first I want to show, you can see that, right? If you can't see it, yell at me. Okay, so this is the example of the accreting simulation. Gas flows in, it hits this magnetic field, and then it's forced to flow along magnetic field lines. And you know that like you can't really see any shocks, anything forming at the surface. It just flows in, hits, and just flows into the inner boundary, okay? And then, okay, let me show you a different one. Okay, this is the 75 albedo simulation, and it starts a little bit, I didn't take the initial condition, I copied it from the Accreting simulation to save some computational time. And this is what this one looks like. So now we're returning 75% of the inflowing energy as outflowing radiation. And you can see that this slows down the gas and it forms a shock, heavy radiation dominated shock. And then radiation is diffusing out the sides of this shock and flowing out along the pulse, basically. And I will just, so you can see it, show you what the reflective simulation, like the fully reflective simulation looks like when no gas, come on, open, when no gas can go through. So you can see the gas sort of just like sits on top until it's blown away by radiation. So actually this gas is like hardly moving around. It's just sort of circulating, and you're filling up this area with more and more radiation until you get these bubbles of radiation which are just escaping. Well, this is kind of an interesting setup, and it's not really what we imagine when we think of accretion onto neutron stars, but it's interesting to study nonetheless. Okay, let's keep moving. Okay, so I showed you movies, but now what I'm showing you are time averages, okay? So, we just averaged the simulation over some time. So you can see just the general shape. So this albedo 0, or this absorbing, has basically nothing going on at the surface. It wasn't basically until 60% that we started to see anything happen. And I don't know if you can see, but there's a very, very faint bright patch on the surface that shows the shock starting to form. You really see the shock much better in this 70%, 75% simulations. And then this, this reflecting one is in this case, this reflecting one is actually not runs as long because I sort of redid the simulations and I'm still computing some things, but basically you see that like now it's much brighter. The accretion column is totally radiation dominated. Okay. So it's interesting to examine some different properties of the accretion column. So what I've done here is I've taken the accretion column, I've drawn some paths which follow magnetic field lines because the gas is flowing along magnetic field lines. And then I've calculated certain quantities along those paths and then averaged them together. So for example, I can calculate the density in the average density in the accretion column. So you have the path length 0, 1, 2, 3, 4, 5, and that corresponds to 0, 1, 2, 3, 4, 5. So you can kind of see how far we're looking at. Okay, so the density of the accreting simulations is much lower. As we increase in albedo, you can see the shock starting to form, and the shock goes higher and higher, and it's pushed to larger and larger radii until we have, in this case, ignore these funny dips, they're not real. The true solution just goes up straight smoothly until you basically have like just like a power law, going back to the accretion disk. Okay. The same thing is visible when you look at the velocity. Okay, you have sort of the opposite. So the highest velocity in the accretion column are these low albedo simulations, and then once you start to turn on the albedo, the velocity is brought down lower and lower and lower, and then it connects back to the accretion column through the shock until you get to this like these truly super reflective boundary conditions, which are basically almost no radial velocity there. We can also see similar behavior in the energy density of radiation, it just increases along with the density. And the flux, this is the flux of radiation, and it also increases, but it's a little bit harder to see. It's a little bit detangled. And then like you would think that the flux is lower, but that's actually because I'm averaging all of these together. And in the radiation, you have gas moving all around. So it appears to actually be much, much lower radially. Okay. It's important to measure the outflows. So I will just show you what they look like. Blue is outflowing gas, and this is like momentum. You can kind of think as momentum. So the accretion and the 75% have, reasonable outflow that is launched somewhere around 25 gravitational radii. And the reflective has tons of outflowing gas because the gas can't go anywhere, and it's very bright here. So you have this interesting circulation patterns that you can't see, and it just launches a much stronger outflow. And the basic idea is that this outflow collimates the radiation in this region. Okay. Let's move on. Okay, this was just a map of the radiation flow. So the color map tells you the magnitude of flux, okay, in the poloidal plane, and the arrows are streamlines of radiation flux. So this shows you like the direction. So the accreting simulation goes, and you can see that the flux appears to me much stronger in the column than anywhere else. And this is related to what I said about super Eddington accretion, that the gas becomes so optically thick that all of the photons can't escape. They are advected with the flow, deposited on the accreting object. And it's only the photons at the surface which are able to diffuse out and escape. Then when you increase the albedo, okay, a shock is formed at the bottom, and this slows down the gas. So it gives the radiation more time to escape. So you can release more photons. So this is why this 75% simulation appears so much brighter. Something similar happens in this fully reflective simulation, but you can see the crazy circularization patterns that are happening because the gas hits the surface and there's nowhere to go. Okay. One thing I wanted to say is that in M1, gas is treated like radiation is treated like a fluid. So radiation leaves the accretion column tangentially, but then it hits the interpolar boundary and is deflected up. Okay, and normally what would happen is, in the full 3D setup, we would have radiation is sort of released, hits the other side of the column, bounces around a little bit, and eventually is collimated. So the true radiation field probably doesn't look like this near the column, but it does eventually become collimated farther away. So it's still a good approximation for what's going on. Okay. Now some details about how to measure the luminosity. To actually figure out how much radiation is leaving the simulations is not super easy to measure. And there's a couple ways you can do it. And to do that, we have to define 3 surfaces. So the first surface is the optical depth as measured radially. So this is, I start from some outer radius and integrate inwards to some radius r of the opacity times density, and I find the r such that this is equal to 1. Okay, and I call that the optical depth as measured radially. You can do the same thing, except instead of like measuring radially, you measure from the polar axis to some theta to, I guess this should technically be r theta, and find when that equals 1. So this is going to tell you how much radiation is kind of moving freely through the column, even though or not through the column, but through this funnel region. And then one last surface is the relativistic Bernoulli equals 0 surface. And basically what this is it tells you whether the gas is energetically bound or unbound. So you would imagine that all of the gas, which is energetically unbound, maybe, sorry, my dog is here. Maybe it will release some radiation, and then all of that radiation reaches the observer. Okay. Okay, sorry, I have to close the door and stop my dog from growling. Okay. This is a similar plot to what I showed before. This is the flux of momentum, but I also included the flux of radiation. And this is for this Albedo 75, which I said we studied in more detail and ran for a much longer time. Okay, so this green line here, this is tau R I was talking about. You integrate radially and find the location where the optical depth equals 1. So that's, and then if we want to compute the luminosity, we could integrate the flux only in regions where the optical depth is less than 1. So we would integrate the flux over this whole region here. And that would give us this one measure of the luminosity called LR. Another way to do it is this using the theta surface. And as I said, you integrate to find this theta surface, you integrate along theta, find when the optical depth equals 1. And then you can integrate the flux along this, in this whole cone. And that will give you the luminosity, this, what I call the theta luminosity, okay? Oops, sorry. Then you can do the same thing with this Bernoulli surface. So this is all the unbound gas. So the idea is you say, let's count all of the radiation flux above this surface and assume that the gas will release all of its radiation at some point. So you can get a luminosity that way as well. And these are these 3 luminosities. You can ignore the pink line. These are those 3 luminosities measured in those 3 different ways. So this LR is like a very good lower limit on the luminosity because you can assume all of this gas will reach the observer without, all of the radiation will reach the observer without scattering off of any photons. Electrons, sorry. Okay, then you can use this theta, which is a proxy for the amount of radiation moving through the column, but there's also some gas which is also moving through the column, which is counted in this measure. So it's possible that that gas could absorb some of that radiation. And that appears to be what's happening here is the gas absorbs the radiation. So the gas gains some momentum, but then the radiation flow loses some energy. And then the gas flow becomes optically thin enough so that it starts to release that radiation again. And so these kind of go off to a constant value. Or constant enough. I mean, it looks like there's a slope, but remember this is logarithmic. So this is roughly constant over 300 gravitational radii. So you can use this, or you could even use this Bernoulli parameter sort of as an upper limit, this as a lower limit. So there's radiation simulation. I saw something between 2.5 and 5. I fixed a couple things with this simulation and ran it again. And I think I actually lowered the luminosity a little bit to about 2, but it's still roughly the same. But this is the total luminosity. And what we want to know is the observed luminosity, okay? So the observed luminosity is, I think I mentioned earlier how you compute it. You just measure the flux and multiply by 4 pi r squared. So that's what I did here. And this plot's a little funny. What this is a polar plot, and the radial component here is telling you the observed isotropic luminosity. And the theta component is the viewing angle. And I'm only going from 0 to pi over 2. So this is like saying, if we're viewing the simulation along pole, like, just straight down, this is the luminosity we see. If we're looking at 10 degrees, this is the luminosity we measure. If we're looking at 70 degrees, this is the luminosity we measure. So you can see that pretty much all of the radiation is confined to within about 20 degrees. And the dimmest one is this fully accreting simulation, which makes sense. And then the brightest one, as would make sense, is this fully reflective surface, okay? And so we see anywhere between 80 and 150, 160 Eddington luminosities from this, okay? And these are the corresponding LRs, this LR I showed you earlier. And it's kind of wild because as you increase the albedo, there's more outflows, so there's more interactions with the outflows, and these two simulations haven't completely converged yet, so I'm not sure what the final results be. It might be flatter and probably a little bit larger luminosities. Okay, but in general, the trend is that they increase, and the lower ones are roughly flat. Okay, so like I said, this 75, these, you can get luminosities between 80 and 160 times the Eddington, which is totally in ULX range. Okay. Then what you can do is you can compute the beaming factor. So the beaming factor is basically telling you, what is the fraction of solid angle that all the radiation is released, or in other words, what is the ratio between the observed isotropic, sort of the inferred isotropic luminosity and the actual luminosity. Okay, so that's just you just take the 4 pi r squared times f and divide it by the whatever you measured. So this is 1 over that quantity. And all of simulations pretty much show relatively the same beaming pattern. You can see that the accreting, the higher albedo simulations, which launch more of an outflow, are more tightly beamed, but they're all, the point is it's all between 1 over 30, 1 over 40, which is extremely beamed. Okay, it's even more beamed and confined than this model I mentioned at the beginning, but some of this could be artificial. Okay, some of this could be effects from this M1 closure. What I'm showing here is essentially the same plot, but just the left half of it from 0 to pi over 2, okay? This is a black hole, okay? And this green line here would be comparable to, I don't think I have a good measure. Okay, this green line is like is this same thing, this isotropic luminosity that I was plotting here. Okay, but it's plotting as a linear plot, not as a polar plot. So you kind of have to work your brain a little bit. So this green line is the result you get from the coral simulation, and these red lines are what happens when you do a proper radiative post-processing, when you actually measure the intensity along all angles and do a radiative transfer calculation. So it drops the this isotropic luminosity by a factor of 2 or 3. So this would be the same as sort of like, increasing the beaming factor, like probably down to, or I guess decreasing 1 over the beaming factor to something like 1 over 10. It's also possible to get an extra factor of 2 from isotropic, from doing a not isotropic, but axisymmetric simulation. So there are some things that will reduce this beaming factor a little bit, but the point is that it's still extremely high. It's still tightly enough beamed to produce these luminosities, which are expected to be observed in ULXs. This is the same plot as before, except for I'm measuring this isotropic luminosity at different radii. And then I'm computing the beaming over here. Again, I'm sorry for the mixed way that I'm presenting the plots. I was just sort of grabbing stuff to put here. And you can get different, the point here is that you can get different values for the beaming depending on what you choose for this true luminosity. So you can get much lower values if you choose to use this LBE, this including all of the radiation, because then you're allowing radiation over a much larger solid angle, okay? But the point is here that even if you, choose the widest possible solid angle, you still get a lot of beaming, okay? So yeah, basically we saw that adding magnetic fields increased our luminosity by a factor of 2, maybe 3. The hard surface can also increase the luminosity by about a factor of 2, at least in the magnetic simulations. All of our simulations showed really strong outflows, which beam the luminosity. We know that the boundary condition has a strong impact on the observed luminosity. We'd say our beaming is consistent with theoretical predictions once you, account for some of these weird numerical things that can happen. So in the future, we're going to consider different magnetic field strengths. I'm working on that right now with another student, Fatima, in our group. Another thing would be useful is to consider rotation. I didn't really consider rotation here because ULXs are rotating slowly enough. I know 1 second pulsation seems pretty fast, but still it's slowly enough so that you don't really have to consider too much the effect as far as the accretion disk is concerned. So I think that's 45 minutes. So it's probably a good place for me to stop and open up for questions. So thank you.
Thank you, David. So do we have any questions? Please raise your hand or type it in the chat. Okay, so in that case, I have a question.
I think I see some hands, Deborah, in the chat.
Oh, okay, sorry. So the show back, please go on.
Hello, can you hear me? I can't. Are you saying something? I can't hear you. Is your microphone on?
Yeah. Yes, but
you can also type it in the chat and I can read it. I can read the question if you write it in the chat. Because I can't hear you, unfortunately.
Okay, so please write it into the chat.
While he's writing, someone else can ask a question if they want.
Anyone else? Okay, so I have a question.
Okay.
It's connected to the microquasar conference when they were saying that maybe your simulations has a low intensity of magnetic field. So do you think that the beaming or the properties will be more consistent with the observation in if the magnetic field will be stronger, or is it possible to simulate it with a stronger magnetic field?
I have simulations so far up to 10 to the 11. I think it's possible to go higher, but I think if you want to get up to these like super high 10 to the 14 magnetic fields, that's going to be out of the question, at least for now. The whole point is to show that we can produce what observations are seen with these low magnetic fields. And the problem is that in order to produce beaming, you need to have a significant outflow. And if you have a strong magnetic field, I think I showed earlier that, hold on, here. I think I showed earlier that the outflow, there is no outflow released in this area where the magnetic field has truncated the accretion flow. So you have that really fine balance between the radius of the magnetosphere and then the radius where outflows start to be launched, because these outflows don't exist forever. They truncate at some radius. In my case, they probably truncate much farther away than I'm even including in the simulation. So the question is, can you sort of strike that balance between the radius of the spherization radius, where the outflows begin, and the magnetospheric radius? So
okay, I'm not sure how they are measuring the strength of the magnetic field. So that, okay.
Yeah, I mean, they're inferring the strength of magnetic field, I guess, from models. So I guess it depends on which model you have, which magnetic field you get. But I'm not an expert in these observations. So maybe in the last couple of years they have some better methods. But from what I know, there's still some people arguing about this.
Okay.
Yeah, and I'm not trying to say that ULXs, pulsating ULXs, have strong magnetic field one way or the other. I'm just demonstrating the possibility that small magnetized neutron stars can produce these large luminosities. Okay, so we have comment from Dilshad finally. Can you comment more?
Can you hear me now?
Yes, we can.
Yeah, finally. Okay. Thank you for the nice talk, actually. Yeah, the question was, can you comment on more on that in the video that you showed that the matter was not falling down because of the magnetic field that you said? And I was wondering, what is the physical explanation of it, and why we should believe that it's the physical, so there is a physical explanation that it's not some numerics?
Well, the gas is falling onto the central body in everything but the fully reflective case. And I am not even saying that the fully reflective simulation is supposed to be a proper physical model for what's going on. It's basically, you have two extremes for what can happen. You can have, the gas falls onto the star, and the star absorbs all of the gas without, releasing any kinetic energy or anything. It just, all the energy goes under the surface of the star, nothing gets out, so the accretion column never fills anything. That's this fully absorbing condition. At the other side, you could have, the gas falls onto the star, and 100% of the kinetic energy has to be released in the form of radiation. Because the gas completely stops. So that's the other extreme, and that's this sort of reflecting thing, and that's just assuming that the surface of the neutron star is so solid that nothing gets through. It just hits it and stops. Probably what's actually true is something in between, where some fraction of the gas falls through and is buried under the surface of the star, but still slows down and releases some fraction of its kinetic energy. So this is why we simulated a range of albedos, a range of the true reflectiveness of this surface, so that the true answer is somewhere between these two extremes. Probably, I can't even say probably, but somewhere we've gotten both sides of we've gotten both sides, which we think are unphysical, and the true physical solution is probably something in between.
Mm-hmm. Thank you. Okay.
Anyone else? So what do you think, Deborah? Should we call it? Okay, well, Deborah, are you there?
Sorry. Okay, I'm here.
I was going to say, it looks like there's no more questions.
Yes, looks like there are no more questions. And in that case, thank you, David, once again for the very nice talk. And next seminar will be next week in person on Thursday at 1 p.m. So see you next week. Thank you.
Thanks, everybody.
Bye.
Thank you.